Okay. So let us start from where we had left off yesterday. Let's start with a 5-minute recap. So we are looking at the history of operating systems, but that history is also telling us some important landmarks. So we started with batch processing systems, where there was only one process or one task in the memory at a time. So only one task was executed as long as it finished. Other tasks could start only when one task has finished. Then people thought that there are two types of operations mainly, CPU operations and I/O. And I/O takes a lot of time because I/O devices are slow. Therefore, when one job is doing I/O, the CPU is basically sitting idle. So can we assign it to some other job? So that led to the concept of multi-programming or spooling, where when one job asked for an I/O request, then it was switched off, as in the CPU was not, I should not say switched off, okay, but yeah, I mean the CPU was not allocated to it at that point when it has asked for I/O. Rather, there were some other processors like I/O processors or some other small devices which helped in this I/O. And at that point, the CPU was allocated to some other task. Right. But still at that point in multi-programming, deallocating one process from the CPU and allocating another process only happened when the first process asked for I/O. And at that point, the systems depended on having a good mixture of processes which will ask for I/O and which will mainly ask for I/O, and processes which will mainly ask for CPU, which used to be called as CPU bound jobs or I/O bound jobs. That worked to a certain extent, but then people tried developing better systems. So then came the era of multitasking, where it was said that we would not wait for a process to ask for an I/O request before deallocating it from the CPU. Rather, we will have a concept of time sharing. So we will divide, say, 1 second into many small parts, and then each part or each quantum would be allocated to one process. Therefore, a process can be deallocated from the CPU even if it has not asked for I/O. So there are two, let's say there are two principal reasons for deallocating a process from the CPU now. One is that the CPU asks for I/O. Sorry, the process asks for I/O operation. Second, its time quantum is over. So now it is the turn of some other process to run. Right? This is time sharing. And we left off at this slide yesterday where we were discussing that there are several requirements now for multitasking. So it's a common knowledge that the more efficient we want a system to be, usually the more complex it becomes. So that is the cost we pay for efficiency. So this slide actually lists some of the costs that come associated with multitasking. So now you need a hardware timer to keep track of how much time a processor has been allocated to a particular process or a job. Okay, before going any further, let me once again tell you that there are some terms which we are using interchangeably. Task, job, application, process. These terms we are using interchangeably. Though I must just tell you that the most formal term is process. Right? So we will, in a future lecture, maybe coming in a couple of weeks, we will understand what exactly a process means, and hence that thereafter we will possibly only use the term process. Right? But for now, assume that all these terms like task, application, process, job, all these terms mean the same thing. Let's just assume for that for now. So we need a hardware timer. Also, we need scheduling algorithms because at a certain point, many tasks or many jobs may be ready for the CPU, which you want to actually allocate the CPU. And we discussed that yesterday. Some of you came up with the answer that just because a job is there in the system may not mean that it is ready for the CPU. Maybe it is waiting for I/O or some other event. right? So there is a scheduling algorithm which keeps track of which jobs are ready and it allocates the CPU to one of those jobs. However, this frequent switching of jobs, which is usually called context switch. So this is another term which we will frequently use. Context switch means switching one process out or deallocating the CPU from one process or job and allocating the CPU to some other job. So this context switch, first of all, it has a high overhead. And second, the context switch happens many times. Right? So as I said, every second may be divided into 1000 milliseconds or even less, I don't. So this context switch may actually happen thousands of times per second. And if an operation happens so many times a second, you have to worry about its overhead. So we have to reduce its overhead. If a task happens only once in a blue moon, then it's okay. Even if it has a high overhead, we usually don't care. But if it happens so frequently, if a task happens so frequently, this context switch, then we have to worry about its overhead. And that is why we care about CPU burst and IO burst. So if a process has been allocated the CPU, it's better for the process also as well as for the whole system that it does a lot of CPU operations. Similarly, if it is doing IO, it is better to do a lot of IO operations in a single burst. And that is why we yesterday were discussing things like in a C program, whenever we write a printf, don't think that the value is immediately printed. Most possibly it is stored in a buffer, and at certain points, when a lot of material has been collected in the buffer, then IO happens. Okay, so there is this concept of CPU burst and IO burst. Right. So these are the three stages that we have discussed: batch processing, multiprogramming, and multitasking. So today's operating systems are multitasking ones, like Unix or Linux. Okay. So let us talk a bit about today's operating systems. So first, I hope this all of you have realized till now that for multitasking, somebody needs to schedule the tasks as time goes. Who will do this? Okay, first written here, kernel does it. But again, understand very carefully that when say process A and process B, or task A and task B, suppose the idea is that now task A will be deallocated from the CPU and task B will be scheduled. But then this cannot happen automatically. Like, first of all, A will not do this. Right? A, you might say A itself should hand over the CPU to B, but no one does that. Like when we write a C program, do we think about handing control to some other process? We don't. So A does not do that. Process A does not do that. So then you might say kernel will do it. Yes, true. But then the CPU is allocated to the kernel. Sorry. At this point, assume that the CPU is allocated to task A. So the kernel is not even running. Therefore, if we say that scheduling should be done by the kernel, then there should be some mechanism so that the CPU is allocated to the kernel. Only then will kernel be able to allocate the CPU to someone else. Second thing to realize is multitasking systems often need a dual mode of operation. We'll just come to this. What does this mean? And thirdly, which we have discussed, a use of timer. So these three are necessities for a multitasking system. Let us understand them. So what is a dual mode of operation? In such systems, a process or a task can execute in two modes: user mode and kernel mode, also called privileged mode. Okay. So at a particular point of time, either the CPU is in user mode or it is in kernel mode, and the CPU knows in which mode it is. Okay. So the user mode is usually used for running normal tasks, things like a C program, things like what we do in a C program, or maybe what a word editor does. Opening a file, accessing memory, closing a file, doing CPU operations, these normal tasks. But there is a kernel or privileged mode, which is used to directly talk to the CPU or peripherals, etc. So I'll explain, but before that, let me ask you, why do you think a privileged mode is at all necessary in such a system? So the word privileged mode should tell you what is written in the next slide, that there will be certain instructions or certain tasks which can only be done in the privileged mode. It's like a normal user versus an admin. So the normal user cannot do certain tasks, but the admin can. In say a web-based system, the admin has more privileges. The admin can do certain tasks which a normal user cannot do. Similar concept is this user mode and kernel mode. So let me ask you, what do you think? Why should a kernel mode be required? Can you think of any tasks which should not be allowed to a normal user but should only be allowed to the kernel? Otherwise, there is no point in having a separate mode, right? So what do you think are some privileged tasks which should be allowed only in kernel mode and not in a normal user mode? Okay, agreed. Killing other processes, modifying system files, process memory allocation. Yeah, agreed. So, okay. What Srihash, Shubham and Rashil has said, they are kind of correct answers. What Achishman has said, RM minus RF star. Okay. You are partly correct, as in surely RM has to access some maybe system programs, but in general, RM by itself is not a privileged instruction. So, for example, suppose I think so all of you have been using Linux system. So say suppose you are in your own directory and then you do RM minus RF star. I think you will be allowed to do it, right? So, but you are right that finally maybe RM will also have to use some privileged mode instructions. But yeah, I mean, try to understand that what Srihash, Shubham and Rashil said, like killing other processes, modifying system files, process memory allocation, they are actually low-level tasks. Right? RM is a slightly high-level task, so I'm not going into that. But yes, so suppose killing other process, no normal user or no normal task should be allowed to suddenly kill other tasks, right? So also think about it. Okay, let me go to the next slide actually. So okay, before that, just one thing that I said that the CPU can operate in two modes and the CPU knows whether it is running in the user mode or kernel mode. How does it know? There is a particular bit provided in the hardware itself, which tells the CPU if it is running in user or kernel mode. Now, as I was saying, there are some privileged instructions, right, which can be run on the CPU only in kernel mode. And such privileged instructions, if you try to run them in the user mode, it will generate some exception. That is, it will not allow, I mean, the CPU will not allow running privileged instructions if it is in the user mode. What are examples of such privileged instructions? Low-level I/O operations, or setting protection registers, or running EI/DI instructions, or enable, disable, interrupt. So here I have another question. See, low-level I/O operations, these are okay. What about this? Running EI/DI instructions. So EI is enable interrupt and DI is disable interrupt. Why do you think these should be privileged instructions? We have discussed the concept of interrupt, right? I assume that you all have a kind of intuition now about what an interrupt means. But now I am asking, why should enabling it? So there are some special instructions like enable interrupt and disable interrupt. Right? So disable interrupt means that for certain amount of time, let's say this instruction is issued, disable interrupt, then the CPU will not acknowledge any interrupts from now on until the enable interrupt is again instruction is again given. So usually the CPU acknowledges an interrupt, like when an interrupt comes, it is understood that some system task is needed to be run. So usually the CPU will acknowledge that interrupt and do something. But there is this concept of disabling interrupt. Right. So if a disable interrupt instruction is run, then the CPU will stop acknowledging interrupts until the enable interrupt is again run. So my question is why? So it's written in this slide that EI, DI instructions are privileged mode instructions. Why do you think they are privileged mode? Okay, there are some answers. Let's see. Exactly. So what Somnath and Ramnivas has said, or even Ayudh has said, that's the idea. So suppose disable interrupt is made a normal user instruction. So then what can happen is that what Raunak has said, yes, some user or some program may do the DI and then forget to do an EI. Right? So it disables interrupt, but then it forgets to enable interrupt. Then that will be a problem. Or what Somnath, Ramnivas, Ayudh has said, maybe there is some malicious program which intentionally executes a disable interrupt operation and then intentionally does not execute an EI. So then what will happen? Remember from what we have discussed earlier that this interrupt is the mechanism by which the CPU will be allocated to some other process. So initially there has to be an interrupt, maybe from the hardware timer, and then the kernel will come into control, and then the CPU will be allocated to some other process. So if a user process is allowed to disable interrupt, all these things can stop, and so that user process will forever be in charge of the CPU. Right. So a malicious process can actually spread havoc. Once it is allocated at the CPU, it disables all interrupts and it forever goes on running. So that cannot be allowed. Therefore, these are usually privileged instructions. Right. So, and yes, like things like killing another process. So suddenly one process or task cannot be allowed to kill another unrelated process or task. That cannot be allowed. Right. So these things are privileged instructions. So again, this is another cost of, say, multitasking, where you need to have some privileged instructions. Now, so we have discussed that the CPU has two modes of operation, user mode and kernel mode. So how to switch between these two modes? Why EI and DI are used? Okay, very good question. If there is so much problem with EI and DI, why even use it? So again, let me ask you first, what do you think? Any answers from your side to Tanmay's question? That why do we at all need EI and DI? Like what can be a practical scenario in which interrupts need to be disabled? Okay, to not heat up the CPU, interesting thought. But let's assume that modern CPUs are advanced enough and so that just getting interrupts will not heat it up. Right, so modern computer systems have good cooling mechanisms, fans. Yeah, you must have heard of these things. So like in interrupt heating up the CPU, it's unlikely. So it's a very valid concern that CPU should not get heated up to a certain extent. A lot of research goes on in that. But then interrupts Heating up the CPU is not a likely event. Okay. Yeah, so any other guesses, as in any other intuitions, like why do you think even interrupts need to be disabled at any point? Why should this need even arise, like disable interrupt? Okay, Pankaj has a good answer. That suppose there are some very important tasks to be completed as soon as possible, so that we don't want interrupts. Okay, normally this is maybe in a normal system this is not so common, but remember that, or you may have heard of it, we discussed also once. There are things like real-time operating systems and so on, where it has to be guaranteed that a particular task must be completed by this deadline. Now, then in those systems, it suddenly cannot be said, oh, you know, that task could not be completed because the CPU was allocated to some other process. That's not a valid thing to say in those kind of operating systems, real-time operating systems. So yes, in certain cases, it may happen that there is a strict deadline by which the task needs to be completed. So interrupts have to be disabled for some time because so that no other job is allocated to CPU. That's possible. Any other intuition? Okay, Shomnath also has a reasonable answer. Like while loading the OS itself, you would not want any interrupt. Okay, sure. Okay, so it's good that you are thinking these things. So yeah, there are certain situations when interrupt may need to be disabled. Also, like we will, yeah, I mean, so there can be certain situations when we have to guarantee that the process will not be reallocated from the CPU. Okay, so in those times, interrupts may need to be disabled for a certain amount of time. Okay, okay. Coming back. Yeah, so how to switch between these two modes, the user mode and the kernel mode. So usually a system call or an interrupt changes the mode to kernel, right? And a special return instruction changes the mode back to user. Okay. But the question is when. Right? So usually we understand that this switch from user mode to kernel mode will happen during a system call. And there will be a special return instruction which will change the mode back to the user mode from kernel mode. But the question is when. So this diagram will try to explain it. Say a user process is running. And the user process does a system call. So a system call, for now consider it as interrupt itself. When does a user process ask for a system call? When it wants to do some operation for which it needs kernel support, like say in IO, or maybe it needs to allocate some memory, or we will discuss these things in the course. It may happen that you are running one process, one task. You actually need to start another task, or your process needs to start another process. Okay, so we will discuss this at a later point of time in the course, that sometimes your process actually wants to create a new process. So when one of these tasks happens, so your user process wants to do one of these tasks like IO or create another process, etc., then it does a system call. And that system call changes the mode, because a system call has to be handled by the kernel. So this system call changes the mode from 1 to 0. Let's assume that we talked about a mode bit. Let's assume that the mode bit is 1 when the CPU is in user mode, and the mode bit is 0 when the CPU is in kernel mode. Okay, so this system call changes the mode from 1 to 0. And then this syscall handler, which is a part of the kernel, this executes. And this does what the request is. So if it is an IO, this will help to do the IO. Maybe this syscall handler will talk with the IO device or the IO controller and then make the IO, etc. Then when this syscall handler has done its job, it will execute a return instruction. And this return instruction will change the mode back to 1. And then this user process resumes its operation. Okay. So the user process has issued a system call, and again, there are many different system calls. In fact, in the next lecture, next week, we will study various types of system calls. So when the user process has done a system call, see again, for the user process, it's just a function call. And again, as I said, the user process may not do it directly. Like when we do a printf statement, our C program is not directly doing a system call. We are using a C library function, but that C library function will actually do a system call because low level IO can only happen with the help of the kernel. So somehow directly or indirectly, the user process does a system call that changes its mode, the mode of the CPU from 1 to 0 or from user to kernel. And then the syscall handler does the job. This is part of the kernel. Then when this job is done, the return instruction is executed. This changes the mode, and then the user process can resume its operation. Okay. Okay, there are a couple of questions. Ayud's question, let me take that first. What does low level IO mean? Basically, actually say reading a key from a keyboard, a key press from a keyboard, or actually printing something to the terminal. Like the printf itself does not do it. Printf needs kernel support. That's why we call low level, as in actually accessing the device. That is what we call low level. So usually we write programs in a high level language. So we all do function calls like printf, like scanf. We can also do a slightly lower level call also, like there are read and write functions offered by Unix, which is a slightly lower level call than printf scanf. We will discuss it in the next lecture. But even then, there is something even lower down, which actually requires talking to maybe a device controller. Right? So that part is low level IO, which definitely has to be done by the kernel. Okay. Abhishek has a question. Is it safe to say that a system call sets and resets mode bit? Yeah, you might say. I mean, at least unless there is a system call, the mode should not change directly. So yeah, I guess, Abhishek, yeah, you can say that. Okay, now Narayan had asked a question. What if a malicious device always raises an interrupt? Okay. Okay, this I am not sure how it will be handled. The device has become malicious and it is continuously raising interrupts. Okay, this I am not sure how it will be handled. Of course, this is not a normal situation. So sure, disable interrupt fine, but see, it's not so easy. First of all, someone, let's say the kernel, has to understand that this device has become malicious. Even how to do that, I am not certain. Right. So how do you distinguish between a device which actually needs some service from the kernel many times versus a malicious device which is forever doing this? I mean, that itself might be a tricky question. And second, suppose in some way the kernel understands it, that this device has become malicious, it simply cannot disable interrupt for everyone. Then there has to be a selective mechanism of disabling interrupt only for that device. Okay, so yeah, I'm really not sure how this can be handled. Okay, it's a good question, but yeah, at this point, I'm not sure. Maybe Moinak, are you here? Moinak, are you here? Okay, I was just I was wanted to see if Moinak has a better answer. But yeah, at this point, I don't have much idea on how this happens. Like a device becoming malicious and always raising an interrupt. By the way, I hope you understand one thing. This question which Narayan has asked is itself a question about a low level device. Think about it. Just your keyboard your keyboard is malfunctioning. It's not at that level. So if your keyboard malfunctions, if some key presses are not working, you simply go to the market and buy a new keyboard. Right. So understand again, your keyboard is a high level concept. Your keyboard is what you see physically. That is not raising an interrupt directly. There is a keyboard controller. Maybe that device is in question. Right. So yeah. So what the question which Narayan asked, I'm interpreting as it's like a internal device, like a keyboard controller. So if that becomes malicious, one thing is it is not working. That's okay. So if a keyboard controller, let's say, is not working, then maybe it will not send any interrupt. Even if you are pressing a key, your keyboard has got damaged. Even if you are pressing a key, it's not being able to send anything to the CPU. That's a different issue. Then you will yourself understand it. You will go to the market, get a new keyboard, you will plug it in, things will work out again. But if a device driver has become malicious and it is always raising an interrupt, like I have never heard of that situation, and yeah, at this point I really don't know how to handle that. Okay, so if any of you also get some article etc., then please point it out to me. But disabling interrupt may not be a solution, because disabling interrupt cannot happen, as far as my knowledge goes. A disable interrupt cannot be selective for one particular device. Okay, let's move on. Okay, so this picture has told us that when a user process does a system call, then the mode changes, etc., and we kind of understand how it works. But then I have a question: is this the only mode? Is this the only situation when mode can change when a user process does a system call? Or based on what we have discussed till now, can you think of another situation where mode can change without a user process doing a system call? Can you think of some other situation where the mode can change even when a user process has not done a system call? Exactly what Shrihas has said, and maybe I would also meant the same thing. A hardware timer interrupt can come, right? So that is exactly what we are discussing. We will discuss next, the timer. Right. So remember, there are two concepts. In one sense, the user process can voluntarily give up control of the CPU by doing a system call. Let's say it's asked for an IO. Then the user process itself is asking for an IO. So it's as if like it is voluntarily. Okay, I'm saying something a bit inaccurate here, but just to understand that, suppose the user process has made a system call, then it is itself asking for a system call. So it is itself asking the kernel to run. So it is you might think that it is voluntarily giving up its hold over the CPU so that the kernel can run. Right. But the another situation which can happen is that, remember, in a time sharing system there is this concept of time quantum. So suppose your process has run for its time quantum. So now it is the turn of some other process to run. Therefore, something should happen which will deallocate your process from the CPU and will allocate some other process. This usually happens via a hardware timer. So how does that happen? Yeah. So recall that a time-sharing operating system will divide tasks into micro tasks and then schedule them in the CPU. So basically, a hardware timer is used to prevent resource hogging or infinite loop, etc. By the way, just one thing, this concept of micro task. See, okay, this is one thing which actually I wanted to say, so let me tell it at this point. So suppose you have written a C program which reads in an array, does a lot of operations, it runs a loop, and then it writes some results, etc., etc. This whole task of your C program is not done continuously, right? So maybe your whole program needs 5 seconds of CPU time. So if okay, let's not talk about IO right now. Okay, just say your program does not do much IO, it only does some CPU operations, but it needs 5 seconds of CPU time. So it will get 5 seconds of CPU time, but not continuously. So maybe it is allocated to the CPU 100 times and deallocated 100 times. And every time it gets like 1/100th of 5 seconds, say 5 milliseconds. 5 millisecond? Yeah. Right. So that is what is meant by a micro task. Now you don't need to worry. Again, remember what we had discussed in the very first week. One job of the operating system is also to make program development easy. So if I tell you today that while writing your C code, you have to remember that your program will not execute continuously. Rather, it will be frequently allocated the CPU, again deallocated, again allocated, again deallocated. You will get afraid. You will say, oh, that's too complex. But then, to our good fortune, we don't have to worry about these things. We think of the whole task as a continuous flow. We don't even understand that our task is not allocated the CPU continuously. So actually, a whole task is broken into several micro tasks, and every time a CPU is allocated to your program, say some micro tasks will be done. Again, it will be allocated out from the CPU. Again, later at some point when it is allocated the CPU, again some more micro tasks will be done, and so on. Right. So your program or any task is not allocated the CPU continuously. So the OS divides, and this part is all handled by the OS. So basically you can assume that the OS divides tasks into micro tasks and then schedules them in the CPU. So how is this hardware timer used? This is important. So the timer is set such that it interrupts the processor after pre-specified time. Who sets the timer? The kernel. Okay. Okay, there is a question I see. How does a message is shown in case of infinite loop or process, that is division by 0? Okay, let me answer that question, then we can discuss the timer. Okay, so Shaumitra's question. Okay. Let's examine the question first. So Shaumitra, can you unmute yourself for a minute?
Yes, sir.
Okay. So your question talks about infinite loop or division by 0. Let me ask you, you have written lots of C programs.
Yes, sir.
If your program has an infinite loop,
Yes.
has ever your process been terminated by the OS?
No.
Think carefully, not only you but everyone. If your program has an infinite loop, has it ever happened that your process has been terminated by the OS? It does not happen. You are in charge of your program. Unless you do something illegal, the OS will not stop you. Running an infinite loop is not illegal. Yes, it's inefficient. Maybe it's a mistake on your part. But from the perspective of an OS, running an infinite loop is not a illegal operation. If by mistake you are running an infinite loop, go ahead. I mean, it's your problem. As in, maybe your process will not do anything useful. It will not give an output. But the OS does not worry. It's fine. Go on running an infinite loop. However, the second part of your question, division by zero. So has it ever happened, Shobitra? That by mistake your program has tried to do a division by zero?
Sir, I don't remember actually, but I think this showed something.
Yes. So if your program does a division by zero, then it's an illegal operation. Then of course the kernel will intervene. So understand carefully the distinction. Don't think infinite loop is like if your program has gone into an infinite loop, then the OS will come and stop you. No. And yes, what Rashid has pointed out is actually true. So many like web servers, etc., they are actually running infinite loops. Right. So think about something like, say, a website or a Gmail, a Google. When does Google end? I mean, that's a stupid question, but I'm trying to say that surely Google is also running a program in the Google server. How long will that go on? Well, ideally it should go on forever. Right. So running infinite loop is not a illegal operation. You may think you did it unintentionally, but running an infinite loop is not a illegal operation. So the OS never intervenes. But yes, division by zero, or like I said, you often get segmentation fault. So these are illegal operations. So usually your program gets a segmentation fault when your program has tried to access a memory location which it should not have accessed. Okay, we can discuss that later. But see, I mean, just to give a very high level idea, we discussed that in such multitasking systems, the memory is actually divided into many programs, right? So many tasks are there in the memory. So every task is allocated only a part of the memory. So your program should only access the part of the memory which is allocated to your program. It should not try to access part of the memory which is allocated to some other program. Okay. So when you do operations like that, which cannot be allowed, then only the OS intervenes. Right. So make this distinction between infinite loop and division by zero. Okay, Narayan is saying running infinite loop heats up my processor. Wow. Then don't run infinite loops or get a better processor. Okay, Narayan, again, jokes apart. So, okay, were you the person who said about heating up? No, someone else. Okay, fine. See, maybe you have a genuine problem with your processor heating up. Fine, but then, yeah, in that case, my advice to you would be, right, get a better server, or I mean, get a better processor, or maybe better cooling mechanism for your processor. Sometimes it happens, like motherboards have only one fan, maybe. Say if you are doing a lot of gaming and things like that, like nowadays people use GPUs. Yes, then it might happen, but then I mean, in general, advice is to go for a better motherboard, which will have some multiple fans, right? But yeah, I mean, running infinite loop hits up my processor. Sure, but I mean, again, so I have not ever heard an operating system stopping a process because it is heating up a processor. Right? Whether it can happen, I don't know. Yes, you are raising some interesting questions because just okay, sorry for the digression. Let me just do a 1 minute. Let me do a 1 minute digression. Actually, in today's world, heating up of computer systems is a very big concern. And don't only think it's about your desktop heating up. Huge, maybe you have heard of things like deep learning. I'm sure many of you do projects on deep learning, etc. So, deep learning, GPUs, etc. It's a big problem for those to heat up. And there are actually a lot of research going on because, to the extent that, some research studies have shown that modern day GPU servers, like the ones which are used by, say, Google, etc., they take a lot of energy, to the extent that they take more energy than a car, like a car running a long distance. They take more energy than even a car. So it's actually a very valid concern in today's world that, processors, like especially GPU processors, etc., are getting too much heated up and they're taking too much energy. So, sure, they are very valid concerns, but in this course, we are not discussing about those concerns. Okay, so we are assuming normal operations where usually heating up of a processor is, it's beyond the scope of this book, this course. If you ever take a advanced course on, say, nature-friendly computing or things like that, which are coming up nowadays, then you would have to worry about heating up a processor and so on. Okay. Another place where you have to worry about these things is mobile systems. Right, a mobile system, say you give an excellent processor to a mobile system and it can do a lot of gaming, etc. But then the mobile becomes so hot that a human being cannot even hold it. Then it will defeat the whole purpose. I think we know that sometimes our mobile phone heat up quite a bit. Right, so if that happens so much that the mobile phone becomes 60 degrees centigrade, a human being cannot even hold it, then it will defeat the whole purpose. So in both very high-end systems like GPU servers and all, heating up is a concern. In very low-end systems like a mobile device, also heating up is a very important concern. So these concerns are there. But then in this course, we are not talking about those things. We are talking about basically small desktop machines, which has one processor. And so heating up of the processor is something which we won't concern ourselves in this course. Okay. But that's a good point, Narayan. But it's out of the scope of this course. Okay. So maybe you might have a word with Rashil, who has some advice for you. Redo your thermal paste. My God. Okay. So maybe you can have a talk with Rashil. Yeah. Okay. And Shubham, yes, what you are telling is possibly correct. But again, let me not go into that because the OS never even tries to detect infinite loops. Like if your process has an infinite loop, it's your issue, as Sir Rashil pointed out. Actually, many processors actually run infinite loops. So an OS will never try to detect infinite loop in your program. Okay, coming back. There's not much time left in the class. Let me just complete this part. So we are talking about the timer. So a timer is basically like an alarm clock. Before going to sleep every night, we set the alarm clock so that it rings at a certain point of time and we wake up. The concept is very similar. The kernel initializes the timer, telling that you interrupt me after this amount of time. And the count value in the timer is decremented by a physical clock. This is important. Don't think that the kernel is decrementing the value in the timer, because again, the kernel will not be running when some other process is running. Okay, so there must be some other mechanism to decrement the value of the timer. There is a physical clock which does that. But the concept is very much like an alarm clock. Timer generates an interrupt when count value is 0. And kernel wakes up upon this interrupt and schedules the next task. Okay. So this concept is very much like an alarm clock. Before we go to sleep, we set the alarm clock so that it rings the alarm after say 6 hours or 7 hours. So that we wake up. Similar concept here, the OS sets or the kernel sets the timer, saying that you raise an interrupt after say 5 milliseconds. And then the kernel hands over the processor to some other process, to some other task. So the kernel has gone to sleep, you might think. The kernel is no longer executing on the processor. The kernel has handed over the processor to some other program and the kernel has gone to sleep. But this timer goes on like an alarm clock. Some physical clock decrements its value regularly. And when the count value reaches 0, then the timer generates an interrupt. This interrupt is like an alarm clock for the kernel. Then the kernel wakes up. And then it has to do the next part. That means maybe it can think that, okay, this process has run its entire quantum. Therefore, let me allocate the processor to some other program now. Okay. Fine. Okay. Fine. So there are a couple of questions. Let's see. So I think Rashil has a comment about detecting loops. Yes, I agree. So again, I don't want to go into that discussion about how to detect infinite loops, because yes, the kernel first of all won't even try to do it, and secondly, there has to be some other mechanism, as in infinite loop cannot be detected by like that. So right. So I'm not going into that discussion about how to detect unintentional infinite loops. Typically, a kernel or OS will not even try to do it. Okay, Soumitra has a question. When a process is going on in CPU, in multitask, if a new job comes, then how to include it in the list of jobs or processes? Okay, good question. Good question, but I have a confusion about this question. Can anyone say what my confusion is? Because I think that confusion someone else also may have from the question itself. Okay, Ramnivas has a question, but okay, let me, in the interest of time, let me just tell you. Okay, exactly. Tanmay and Pankaj is pointing out what my confusion also is. So some job is running on the processor. How does the new job even come at this point? Yeah. So Tanmay, Pankaj, Akshat, they are asking the same question, which is my confusion also. One process is going on in the CPU. How does a new job even come now? So again, Soumitra, see, the issue is this. When one job is going on, another job cannot come. But yes, we forever do that, right? Say we issue a print operation. We ask someone to open a file. We double click on a file and we ask you to open it. Exactly. So that is the thing. When a user opens a new application. So the thing is, first of all, understand that as a user, you are using an application. First of all, let's assume that application is running at this point. So say you are running Microsoft Word. You are running Microsoft Word and you are trying to issue a print operation. So let's assume that at this very point, Microsoft Word is executing on the processor. So yes, then you issue say a print operation. Of course, that's a very high level operation, but suppose you do that. So then what will happen? Microsoft Word is executing now. It will at some point issue a system call because it needs to print out something. So then it will possibly hand over the CPU to some other process. Basically, the kernel will start running and it will. So your program, say Microsoft Word, has asked for an IO operation. Therefore, the CPU will be allocated to someone else. But again, understand when one process is going on, suddenly another process cannot come. You can introduce another process in the system. And we will actually talk about that in the course. Like your process can actually create a new process. We will discuss how to do that. That's a very common operation, like your process creating a new process. That can happen. But for that, first of all, that CPU must have been allocated to your process then. Otherwise, your process could not have allocated a new process. Right, I hope that clears your answer. So again, it's an illusion that so many processes are running together. Yes, Soumitra, unmute yourself.
Sir, I am not saying that the CPU is allocated to a different job, but in multitasking, the OS has to handle many processes. Means so that's why switching occurs. The kernel has to schedule it to different job, and I am saying that suppose a job is going on in CPU, then a new work comes. So who will include
Comes from where?
from the user?
Are yaar. See again, one job is running on, suppose application A is running on the CPU.
Yes, sir.
Do you think some other application at this point can introduce a new job?
I am not getting that actually. There is my confusion. Means how the work happens.
Okay, so fine. So okay, so suppose program A is running. The CPU is allocated to the program A now. Only A can do some action. So if a new job has to come, then A must be the one to introduce it. We are talking about a uniprocessor system, so there is only one. Okay, Shoumitro, keep yourself unmuted. Let's discuss this because others also can have the same doubt. So let's discuss for 5 minutes. So processor is currently allocated to process A. Only A can run its instructions. So processor is just fetching the next instruction from A and running it. At this point, neither the kernel is running nor any other application is running. Okay. So now frame your question. See, framing the question better may actually make you understand the answer also. So can you frame your question better? What do you want to know? I mean, just don't say I am not understanding, but try to tell what you are not understanding. What is your doubt?
Sir, suppose a process is going on A. So it's the CPU is doing job for A. After the timer interrupt, or suppose timer interrupt, the mode will go to the kernel. Then kernel can switch the CPU to a different job.
Yes.
So kernel have then something that there are three types of jobs. Say for example A, B, and C.
Of course, kernel knows how many
Yeah.
jobs are there in the system. Of
So
course.
so the jobs are definitely coming from the user.
Yes. True.
So suppose a job is going on in
User,
CPU.
again, see, instead
Yes, sir.
of, sure, the job is coming from the user, but a slightly more technical way of putting it is one application is starting another application, maybe.
Yes, it can happen, but
Yeah.
the user
It
can
can
also.
happen means that is what happens. See, you cannot access the memory and then introduce another job by yourself, by your hand. You
Yes, sir.
must use one program to start another program. Okay. So sure, okay, you can say that user is introducing at an abstract level, but understand that one application is starting another application maybe. Yeah,
So
go
which
on.
application is starting? That one which is currently going on in CPU.
What is any other choice? An
Okay.
application which is not even running, how can it introduce another job?
Okay, sir.
Okay.
Okay.
So an application, see, starting a job is an operation, and to do any operation, a process has to have the CPU. Unless
Yes.
a process has a CPU, unless a process is currently running in the CPU, it cannot do anything.
Okay.
And this is true even for the kernel. The kernel also, in order to do anything, in order to schedule a process, etc., it has to be executing on the CPU. Right, so one application can start another application only when it itself is running on the CPU. Is this okay?
Okay, sir.
Okay. So do not think that when application A is running, suddenly some other application can introduce another job. Impossible, because that other application is not even running. Right. Again, see, we might think that, hey, well, we can start a new application whenever we want. We don't have to wait for someone. Sure, but that is an illusion which the OS is giving us. This whole GUI. is an illusion when this process is giving us, the OS is giving us. The things are switching from one process to another so fast that we as a human being won't even understand that the GUI program is not running always. So we think that, oh, whenever we are clicking on whenever we are doing a mouse click, a new application is starting. But that whenever if you go down to kernel level, etc., that whenever must happen when that application is actually allocated on the CPU. Otherwise, one application cannot even start another application. Okay. Okay, fine. So yeah, let's end this class today. We will continue again next week. Thanks everyone.